HybridDigital, we tried to bring out our data to a level to be fair, and we tried different methods and approaches therein. And today I want to give you an overview about our lessons learned. So which of those approaches worked as expected, which of them didn't work as expected. And also I want to show why it is worth to actually do fair data by showing some demo applications from our demonstrator. The next, I think, 45 minutes, we will see, first of all, the motivations, what was the actual problem, which use cases did we derive from this, and what was the overall approach. Then which data did we generate, so from experiments and from simulations, and how did we store them. Third point will be the actual fair data pipeline. So how do we come from raw data like Excel files to fair data structured in an ontology, or hopefully fair data. And finally, we will have a look at the use cases in our demonstrator. Let's start with the motivation. So in the project, we addressed the material combination of CFRP, which is the black thing here. This is carbon fiber reinforced plastics. And we combined this with metal structures. That's the silver thing here. And in this way, we did it using adhesives. The second approach, which is possible, is to use just bolts. And this combination of materials is used mainly in automotive applications, in premium cars and in aerospace applications, because it just offers really, really good high performance material characteristics. So those are the materials that we addressed in the project. Problems that arrive with these materials are mainly two categories. The first one is the engineering and the construction. So if you have a look at such a hybrid material, you just have to consider a lot of factors for the engineering, like, for example, the layup of the CFRP, so how the carbon fibers are oriented, or which material should I use? Should I use an adhesive, or should I use a bolt? How far, or what should be the length of the overlap? So there's just a bunch of factors that you need to know about if you design such a material. The second problem category or challenge is the actual manufacturing. So you combine two materials. So you apply, for example, the adhesive. You have to know, how should I prepare the surfaces? So should I just wipe it with alcohol, or should I sandblast it, for example? Then you have your adhesive glued material. You put it into an autoclave, so like a pressurized oven. There you need to set the temperature, the pressure, and so on. And also here you have a lot of influencing factors on your final product, which you have to be aware of, to consider them. Based on these challenges, we developed 5 use cases together with this consortium. We had Cortesa. It's a leading manufacturer of CFRP structures, mainly in aviation. We had Novicos, which did a lot of structural simulations. Ineri, they focused mainly on machine learning and providing different cloud platform technologies. We had the Fraunhofer IGCV, where I am employed. We focused on the composite processing and in setting up the whole ontology infrastructure. We had Hochschule Aalen, which did all the material testing, and finally the Fraunhofer IDMT, which focused also on machine learning in this project. Together in this consortium, we asked us what should be done actually with our tool. So what, why, which. And in this case, we had 5 user stories or 5 use cases. The first one is the digital part record. So we want to follow a manufactured hybrid material part and ask, for example, what was the temperature or what was the material used for exactly this part which I have here in my hands. The second use case was anomaly detection. So let's assume you manufacture one batch of parts or specimens and they differ in some attributes from another batch that you manufactured. And now you want to know why actually, or what are the differences. The first use case is the correlation analysis, which should help you to understand the whole process line better by asking factors are affected if I change something. For example, if I change the bolt diameter, which factors are affected in the material characteristics? The fourth use case is the engineering assistance, here with this robot with a fancy haircut. Here I want to know how should I actually design my part or parts of my design, like for example the overlap length, in order to reach a given material characteristic or a given performance. And finally, we have the processing assistance, where I want to know which parameters should I set, for example, for the temperature of the autoclave. So it's more focusing on the manufacturing. Those, sorry, those have been the 5 use cases that we addressed in the project. And that's one of the first lessons learned. We did those user stories, but we did them late and we didn't maintain them perfectly in this project. So I can just wish you, if you have an upcoming academic project dealing with ontologies, always create user stories as early as possible, because we do things, so we do develop ontologies, fair data stuff for applications, for users. So the users are boss, lastly. And how should we do this, or how should we have done this better? Just by using interviews. So really asking the people who have problems at their machines, what are actually your problems? What could also solve your problems? So what is the system that you would wish in your dreams? This is targeting then the front end. Finally, why should we use user stories? It's three benefits. Lastly, first of all, it helps you to at least approximate which information do you have to measure along your whole processing chain. It helps you also to identify or to get clear about which objects do I have to uniquely identify. For example, for us, it was necessary to give each hybrid specimen a unique ID, like a serial number, but it was also necessary to give each manufactured CFRP part or every steel plate a unique ID. And if you do not know this from the start of your processing chain, you're actually lost at the end, because you might not be able to bring back your data to the actual objects. The third one is it helps you to structure your infrastructure, because you can then at least approximate, will it be enough to actually just query information, for example, for the digital part record, or will I need to use further statistical methods or, for example, machine learning in order to build up correlations in order to fulfill my user story? So I just can encourage you to use user stories as early as possible. The main approach now in the project is we have a lot of unstructured raw data from experiments and simulations, as we will see later. Currently, it's 7,000 files in the project. Using this, we create fair data using an ontology. And then using those fair data, we do classical data analysis and machine learning in order to serve our different use cases. In this case, where we created a web application for the end users. So let's go now step by step through this approach, through these steps. We start with the data generation. How did we do this? And how did we store those data? We had three main sources of data and information. The first one is the manufacturing, where we just collected different information. Why did we do this? Because from the user stories, we knew we have to build some correlations. For example, from the curing temperature to the tensile strength of the material. So we require just sets of configurations and how they correlate to the tensile strength. And this is why we collected information, for example, about the curing temperature during the processing. What and in which format did we do this? For example, the curing temperature, it was just an output of every curing cycle as a time series in CSV format. Or for example, the type of surface preparation. So was this part wiped with alcohol or sandblasted, was just captured using an Excel file. So this is not fancy, but it worked in this case. And just using this approaches, we just collected a bunch of data and information along the manufacturing. The second source of data and information were simulations. We see here two models. The upper one is the bolted simulation model, the lower one, the adhesive bonded specimen. They've been created by Novicos. Also here, why did we do this? Because we knew we need to do correlations between configurations and results, for example, bolt diameter and tensile strength. And we are not able to either capture some information using experiments, or we are just not capable to do enough experiments to generate enough data. So we did it using simulations. What and in which format? Also here, we just communicated, so Fraunhofer and Novicos, and for each simulation run, they outputted one JSON file where they describe their configuration, like the geometry, the bolt diameter, the material characteristics, and one result file, in this case a CSV, where you just have your displacement, force, and stress curves. That's the second data source. The third one is the material characterization, which did the Hochschule, and there they did a lot of tensile tests and different types of other testings. We did it again because this is one of the target variables in our user stories. And also here we had different formats, like for example, a CSV with the tensile test results, so the time and the displacement and the force and so on. One lesson learned from this, again, is care for the chain of identification. So ensure from the start of your processing chain which objects and even processes do you actually have to uniquely identify using serial numbers or other number formats or identification mechanisms. And yeah, I think for bringing this all to an industry ready, there might be better approaches than we did in future. We have now the raw data, and we used an Azure Blob Storage, in this case from Microsoft, where all the different project partners just put the raw files in a directory structure, which we just communicated internally so that everybody knows where to put which type of data, for example, the results of the tensile tests. The lessons learned here is the blob storage worked pretty fine for us, but again, bringing the whole system infrastructure to productive readiness would require to also account for other types of data sources, like, let's say, Google Drive or so, or directly the machines, because the current implementation doesn't account for this. So it fixes really on this blob storage. It must be more flexible in future. We now have the files, the raw sources, and now we will have a look at how do we come from the raw sources to the hopefully fair data using ontologies. And we will go now step by step through this pipeline. So on the right side, we want to have the fair data in GraphDB. We used GraphDB here as a triple store, and on the left side, we have the raw files. The first step in this pipeline is to actually capture every file which is stored in this Azure Blob Storage, and also track how it changes over time. I call it semantic Git in this case, just for example. So let's assume we have a user from a project partner which uploaded a CSV file to the Azure Blob Storage. Then there's a Python script which checks that there is a new file in the Azure Blob Storage and creates in the triple store a new node, an instance of a specific file type in the triple store, and also creates some meta information like the date it was uploaded, or also the path where you can really find this file. Now let's assume the file changes over time. So people change information, they add columns, for example, to a CSV or an Excel file. What happens then? Same principle. You have the changed file. There's a Python script which checks, oh, this file is changed, and adds now a new node, a new instance to the triple store for this changed file, and links this node to the old file, now just using an object property in this case, like replaces. So using this, we just capture the evolution of different files, and also to know just which files do we have. Lessons learned here, this file change management is somehow essential because files will change, and if you want to have fair data, you somehow have to address this, that they are not static. But the current implementation, mainly regarding performance, may need rework to really get production ready. And also, not all information in companies is stored in files. You also have like SQL tables or so. So the same approach must be adapted to other formats, not only to files. After this step, so we know which files, or for each file, we create a node in the fair data. After this, we have so-called parsers in this case. A parser actually reads in a file and outputs a JSON. That's all what it does. So currently in the fair data, we have just the information about the files. So we also know which files have not been processed so far. So search for all files which are leaf nodes, more or less. And then try using those parser modules to read in and output a JSON. A parser module is a separate Python script which always checks if a file is valid for this parser. For example, if it has a specific file format or contains specific columns in a spreadsheet. If this is the case, it reads in the data and outputs a more or less hard-coded JSON structure. If this is done, or in general, every parser script is versioned using GitLab. So there you can find what this parser does. And if a parser parsed a specific file, also this information is added to the triple store, so that this parser parsed this red file here, file B, and also the version of this parser. What happens if the parser changes? the same as with the files. So if the parser changes, the new parser parses the old file, and also this information is added to the triple store, so that the new parser replaces the old parser and now parses the old file. So we also track this. One problem is inflexibility. Let's assume on day one we had a spreadsheet with 2 columns, density and the part ID. The parser reads it in, outputs a JSON. Cool. Next day, the column names changed. The parser was hard-coded to search for specific column names, and now it fails. One solution for this are large language model microservices, which was just a side branch in the project. So it was just for testing, but it worked pretty good actually. For example, the parser now not uses hard-coded column names, but just gives the advice to a large language model, search for columns which indicate density and the part ID, and then you get the output. Or for example, we had several test results with a column where the tester mentioned if the test is valid or not using a comment. And also here, we just used a large language model, which then decides, yes, it was valid or not. And here in the parser, so this modular structure in the parser just helps to split this whole process down into singles or simpler steps to let this do by large language model in future. As I told you, this was just a side branch. We have the parsers now, and we have the information which parser parsed which file. Why do we need those parsers? We need them in order to somehow address that files might change. So we also have to somehow version the parsers. The use cases in future might need other information extracted from the files as it was 2 weeks ago. So at week 1, you might need column A and B, but 2 weeks later, you might need A, B, and D, for example. And this can be done just using those parsers. There might be errors in old implementations, which you might detect 2 years later. Then you can just adapt this parser and rerun it again. And yeah, it's just important to also, according to my opinion, to track those changes also in your fair data. Lessons learned here are, it makes, according to my opinion, totally sense to split this into the source, the pre-processing, so into the reading and outputting a formatted structure, in this case JSON, and then do the actual modeling. Also, the versioning is important, according to my opinion. A problem is the bad performance. So currently, every parser script tries to match with every file, which is just brute force, more or less. So in future, I'm really sure that there are a better ways to do this parser file matching for a production-ready approach. And one question then also is, who actually will create in a production-ready tool those parsers? So is it like the IT department, or is it the guy who does settings at the machine? That's just the questions which stay open in this case. We have now the files, they get read by the parsers, they output JSONs, and now we have so-called generators or connectors. A connector takes as an input the JSON output of the parser. Currently in the fair data, we just have nodes for parsers and nodes for files. And then there are also separate generator or connector scripts, which check, can I use this JSON as an input and actually create the content triples? So here, the actual triples with creating the instances of classes are done. We used in the project the BFO as an upper ontology and the CCO as a mid-level ontology, and this worked actually pretty good. If now a generator script creates actual content triples, this is uploaded to the triple store in this way. First of all, also a node is created for this generator script, indicating its version and so on. And then the actual content triples are appended to this node, to the script, as a named graph. So in this named graph, then the actual triples indicating this is a specimen, it was input with a tensile test and had a force and a strain and so on, is appended as a named graph in this case. This results in the following. So you will have one named graph indicating the tensile test, the strain. Then 2 weeks later, the generator script changed, maybe because there was an error in it or so, or you changed your modeling behavior. So new triples are created and the link between the both generator scripts, and also the same for rules, which we will come to later. For querying, I only want to have the most latest triples. I don't want to work with the bad old information. So there's always one named graph, I just call it productive graph, which is the sum of all latest triples in this case. So the red marked area here. And all queries for the digital part record and so on are always done on this productive graph. So on the most up-to-date triples. Why do we need those connectors? The parser outputs might change because the files had changed or the parsers itself. So we somehow need to work with this flexibility. The modeling patterns might change. So let's say you worked with BFO for 10 days, and after that you decide to use Dolce. Now you just have to change your generators in this case, or again, errors in old implementations. Lessons learned here, the whole approach brings just a lot of flexibility to it, but there are still different things to think about. For example, how to identify uniquely instances in the ontology. So, for example, a generator script might search a specimen by its ID. So there's a Python function which gets the ID and actually does the querying to the triple store. But this is just a little bit fuzzy. So if you think now about a huge company, the modeling will get bigger and bigger. So I think the implementation here should be better in future or more modular even. Same problem here as for the parser. The parser to the connector matching is currently not too performant. So also I think there are just better ways to do than the brute force approach that we do currently. And also I think it's an issue with GraphDB, or at least I think so. You cannot do reasoning in named graphs, what is not too easy then. And also to have the productive graph as a named graph brings some problems. So in future, I would just create a new repository for all latest triples and keep it totally separate from the old triples and just have links between both. Last step in the pipeline are the rules. Rules are also modular, and let's assume we have the triple have triples in the triple store, which indicate a specific standard has been used for the tensile testing of a laminate. Then there are separate rules, also as Python scripts, which search for patterns and add further triples. For example, here the ply stacking of the CFRP based on the standard. Or, for example, search for densities of the carbon fibers, and for the polymer, if you find it, calculate the fiber volume content and append the triples. Or if you find a specimen which has a force and a surface area, calculate the stress and append it. So also here, every rule is just versioned using Git. That's the whole pipeline. Summarized, we have the raw files, which get tracked in the FAIR data. They get parsed by parsers, which create JSON files, which is contained in the FAIR data. Then the JSON files are read in by connector scripts, which create the actual content triples, and we have rules which add further triples based on more general rules in this case. With this approach, currently in the project, we have about 40 million triples, which is still okay for running the whole system. Let's finally come to the use case demonstrations. The first one is the digital part record. So here I want to know specific material properties or processing information for a given part. Let's see how this looks. I have to check. Okay. So we host a web application here at the Fraunhofer IGCV computing cluster, and if you want to access the web application, you need to be connected to a VPN. If you do so, you can go to this web application where you have 4 apps in this case. For the digital part record, you here enter the part ID, so like the serial number of your part. We copy it in, and then you can search. In the background now the information are queried from the triple store and then just visualized here, like for example the history or the curing temperature of the adhesive, ID of the CFRP plate, the method of surface preparation, or the results of the tensile test in this case. The same can be done also for simulated specimen. So also they carry a unique ID, which you can then query and get other or the same information. For example, here the ply stacking of the CFRP, or also the simulated tensile test results in here. To the modeling here between experiments and simulation, they are done exactly the same. So it doesn't matter if a specimen is simulated or done in physical reality. There's just like a tag to a named graph that this is synthetic data, so that all triples out of this named graph are out of a simulation. And currently, at least for those cases, it works pretty good. This is how it looks for the digital part record. Again, the background, there's a Sparkle query where the part ID gets filled in, it gets sent to the triple store, and then the result gets visualized in the front end where we used Angular in this case. Lessons learned. This works good currently, but the query formulation is pretty hard to do. So that's a huge query. And if we think about a more flexible production-ready implementation, it might be necessary to update this regularly in a faster cycle. So to also get informed, for example, if there are new kind of information available along the processing history. So I think this would be something which could be done better in future. For all other use cases which follow now, we do not work directly with the graph data, but we export them to a tabular structure that looks like this. There's one master boss Sparkle query, which is done in a specific given time interval. So let's say every day. The query is sent to the triple store, and as an output, we just get a big table. So it has about, I think, 60 columns, and every row represents one specimen in this case. And this big table is then uploaded as a JSON file to the blob storage. Why did we do this? Because all further processing of the information just requires either tabular data as an input, or it requires this for performance reasons. a lessons learned here, or lesson learned here, is all further processing is performant, but it's hard to scale, because again, here you have the Sparklet query, which you hard code at least for a given time. So this must be more flexible in future. And also you lose information due to the transformation of the graph to the table. For example, the whole class structure, also the object properties. In future, I want to try then to use graph neural networks, and also tested it. It should, at least to my opinion, work better, because you then might be able to benefit or problems on the left side. Let's see now at the use cases. The second one was you want to know why two batches of parts or specimens differ from each other. Also here we can look at the web application. You go to material dashboard here, and here at the top you can select which information you want to see on the X and Y axis here at the bottom. So currently it's selected, you want to see on the X-axis the surface preparation of the composite material, but you could select a lot of other stuff like the bolt diameter, for example, temperatures, and so on. The same for the Y-axis. Currently, we now see on the Y-axis the tensile strength, and here on the X-axis the surface preparation methods, like removing just the peel ply, do laser roughening, sandblasting, etc. Let's assume now you have manufactured different specimens or parts with adhesive, and you see there are differences between those batches. So now you filter to just see specimens which use an adhesive. So I filter here, contains a bolt, no. But now we see only the specimens which contain adhesive. We see now we have somehow two clusters. The first one, or here are some specimens with which have a high tensile strength, and here some with low tensile strength. And now I want to know why. In order to do so, you can just select those two clusters. See if it works. Yes. And those are the bad ones. And you name those if you want. I call the green ones the good ones, because they have high tensile strength, and the bad ones are the yellow ones with low tensile strength. Then you can click here, compare clusters, and you get on the left side information or factors which are common between the good and the bad ones, and on the right side factors which are differing between the good ones and the bad ones. The shared commonalities are, for example, contains bolt, no specimen of the good charge, and no specimen of the bad charge contains a bolt. That's clear before, because we filtered for this. And also, for example, what do we have here? The adhesive, the tensile strength of the adhesive is nearly the same for both. If we go to the differences, we also here get a ranked, ordered list with only the high influencing differences in this case, or the high scaled differences. And we see here we have the mean curing temperature, where the good ones had a bigger value than the bad ones. The same for the maximum curing temperature. What else do we have? We have the tensile strength of the good ones is bigger than the bad ones. Well, that's what we actually expect, because we built the clusters by that. But if you look here, you get the information that the good ones use a mean curing temperature of 125 degrees, and the bad ones in mean 80 degrees. And this is exactly what happened in the project. So this was more or less an error, and those specimens have been cured using too low temperatures. And so it might help you at least to come to this conclusion by using this ordered and ranked overview of information. How is this done in the backend? As I told you, we have this big table. The user selects the groups, and each data point is in the backend or the background linked to the actual part. So we can more or less build the groups using the rows. And then we apply a combination of different statistical measures, like we have different data formats here, or data types, like Boolean data, numeric values, and categorical values. And using a combination of classic statistic methods, we can do this ranking. What are the commonalities and what are the differences? And then we visualize the result in the front end. The third use case is the correlation analysis, where I want to know which factor affects other factors. We also can have a look here. You go to correlation analyzer and select here the target variable. So for example, you might select the bolt diameter, and then you get an ranked overview with which factors does this factor correlate. Let's select the tensile strength, because this is in many use cases the target variable. You can see that the tensile strength correlates 100% with the maximum force during tensile test. That's what we expect. Then we have here the tensile strength of the adhesive, and you always can click on one of those factors and you get the visualization of the actual raw data points. And here you can see those nice linear correlation between the tensile strength of the adhesive and the tensile strength of the whole hybrid material. Or further correlating, highly correlating factors, for example, the friction between the steel and the CFRP. Those are all information from simulations. And so you can go down, 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 and you have non-correlating factors here. Here it's important, correlation does not mean causal connection. So there might be correlations which are not actually in causal relationships, that this stays up in the user to decide. How is this done? Also here, we use this big table, and for each combination of two columns here, we build subgroups where all configurations are the same. So for example, where all specimens used adhesive and where all specimens came from simulations. So after this, you have just a bunch of different subgroups built out of your data table. Then within each subgroup, you correlate or you calculate the actual correlation. In this case, just a simple linear correlation, Spearman. Then you more or less average all those correlations between all subgroups. And then you do the same for all combinations lastly. Out of this, you get a correlation matrix, and this is then visualized in the front end. So more or less one column of this correlation matrix. And all this path here is done to find true correlations, so to avoid to use correlations which have totally different configurations by building automatically those subgroups. Lesson learned here is this works pretty good, and there are no or nearly no hard-coded aspects in this pipeline, so this is scalable. That's pretty good. Finally, a look at the time. We have the engineering assistance where you want to predict something. I also can show this. So You go to predict performance. You select here the value that you want to predict. This is currently under development, so Inari trains, again, based on this big table, different machine learning models in order to predict the target variable. Let's select here, it's an academic example, but it works, mean force in tensor strength. Here you set up your configuration, like the way the surface was prepared. Here the strain, as I told you, this is an academic example. What you would select, it's under construction, is here the same, but you want to predict, for example, the temperature to use. Go and predict. In the background, Inari hosts different machine learning models which get called, and then you get your predictions based on experimental results, based on simulations, and based on the combined ones. So here's a model trained only on the experimental results, here only on the simulations, and here the combined model. Okay, I think that's it. So to summarize, these have been the use cases. It's pretty complex, those fair pipeline thingies. Takeaways are create user stories as early as possible. They help a lot. This split between the source, the pre-processing, and the modeling makes sense, according to my opinion, and also the versioning. Fair data are a fantastic base for most use cases in here, because also if we extract those this table, the step itself is pretty easy, and not every use case must be inside of an ontology. So the ontology itself can be just also like a pre-processing step for machine learning. And it's still a long way to production readiness, for at least for this approach, and the LLMs might be a chance. The good thing is we are also part of HybridDigital 3 with Moby Dick. It does not have to do anything with whales, but I just like this whale. And here we actually want to address all those gaps that I mentioned the last 45 minutes and try to bring this into a production ready approach. And yeah, so with this, I want to end and thank you. I hope there might be some interesting aspects that you can use in future. Thank you.